So again, this is not meant to be comprehensive, just a few things which sort of effectively came to mind as important, interesting discussion items. So I guess maybe put this on, but let's see. So let's get to the. Do we have the? Yeah, we're on the wrong. Let's get the right. Let's get the right. Let's get a more of a discussion up here. Okay, so so one thing I thought would be interesting to discuss is one thing from the frontier field that we're starting to be able to potentially probe is what the volume density of these ultimate galaxies are, and so we can start to come up with some indication of what the volume density is and how it might evolve in cosmic time. And I'm going to say a few words on this, and then I would be interested to hear what can be learned from various archaeological studies, because I think that maybe there's some. And it's interesting because it basically results in some puzzles which various there were some attempts to solve it in various ways. So basically, from the Hubble Frontier Fields program, allows us with gravitational lensing to reach very faint objects, and so in principle allows us to go down to minus 13th magnitude. There's some uncertainties, obviously, in doing this, which I highlighted in my talk, but we'll just ignore those for the most part and just get into the discussion items. So most of you are used to looking at the bright end, how the UV luminosity function or the luminosity density evolves at the bright end. And so we'll just ignore the dust-obscured stuff and then just look at, this is basically for the brightest objects. And there, the evolution tends to be a little bit more rapid with cosmic time, particularly at high redshifts. In thinking about cosmic reionization, we see this very rapid, potentially rapid evolution at early times. And so, however, once you go down further down the luminosity function, it turns out that this very rapid evolution becomes much less rapid. And so if you would just take, say, some of the results from the field, here's my own compilation. This is still not published, but basically preliminary results. And if you just take these results and sort of say, okay, let's this is basically extend this to sort of fainter magnitudes, and then kind of extrapolate the results, what you get is that when you get down to minus 13th magnitude, at least if you do the extrapolation, you get to a point where there's, in principle, not a lot of evolution. And so what ends up happening is basically, I didn't have a plot showing exactly in the same scale because I was having to try to throw this thing together basically during the afternoon session. Basically, if you do this and you look at the evolution of the luminosity density, these are in various slices. This is a bright slice. This is a slightly fainter slice. Basically, at the very faint end, this is just an extrapolation of my field luminosity function results based upon the basically candles and the UDF. Basically, you get about no evolution in terms of the luminosity density from UV luminosity density between, say, redshift 4 and redshift 8. And so a lot of the preliminary results from the Hubble Frontier Field programs are pretty consistent with this. And this is basically just due to the fact that you're correcting the evolution of the bright end of the luminosity function with the fact that the luminosity function is steepening. Now, so basically, if you look at the UV luminosity density, there's not a lot of evolution here. However, if you would actually look at the results from that you would infer from various prominent observables, say from Planck, from various other observables. So one thing that I did in my presentation last year is you can actually take a lot of these observables and from Planck optical depths, when does the universe get reionized, some constraints from the Lyman alpha prevalence at higher redshift, basically connecting with this, the various results in the Lyman alpha forest. And I can, well, if anyone want to hear about that again, I didn't want to go through that presentation again. But you can essentially go through and take all these observables and invert them and essentially come up with a constraint on the evolution of the ionizing emissivity. And these are updated for basically Planck 2016. So basically Planck 2016, these are basically the evolution. Now the interesting thing about this evolution is this is very different than the evolution that you get for, so that, this is what we did from last year's talk. You can do this basically by essentially assuming that, by trying to essentially match these constraints, taking essentially, assuming that the ionizing emissivity is equal to a constant, modeling this with a constant and essentially a redshift-dependent component, and then essentially marginalizing over everything to get a good match to the observation. So this is what happened last year, and you basically get this curve. So the interesting thing is that this evolution that you need to essentially match all these observables, and in particular the very low value of tau from Planck that basically was just reported, it shows a very steep evolution relative to basically what you get from galaxies, from very faint galaxies. So if you take this galaxy interval and this galaxy interval, it's very, very flat. And so, interestingly, so if you assume a constant Lyman continuum production efficiency and you put everything on the same plot, you basically get that basically what you need to match constraints is very steeply evolving, and what we infer is the situation is from basically looking at the luminosity functions, a very flat evolution. So very steep, implied by looking at various things like Planck tau, when does the universe get reionized, various things from looking for the Lyman alpha prevalence at redshift 7 and 8. And basically the observations would suggest almost no evolution. Now, so again, these look very different. So basically, there's how can you reconcile these things? There's different ways. You could, in principle, assume that maybe there's some suppression of low-mass galaxies at redshift greater than 6. I think this is going to be difficult to probe. The other way, and I think this was suggested by Steve's talk, and probably how he basically tried to get everything to fit, is basically you could also introduce, in addition to galaxies, a quasar component, where instead of having basically a flat evolution with cosmic time, you basically, and this is just taking everything, putting it on the same scale, you basically get this evolution like this. You basically assume that the quasars evolve in such a way to essentially match what you require from Planck. However, let's just whatever, saying that basically, I think that it's going to be very difficult it's going to be difficult to essentially test. So the one way of explaining this is using quasars. I think it's going to be difficult to probe observationally. Another way is potentially by suppressing the star formation of low-mass galaxies. I think this is also going to be difficult to probe with the frontier fields, because I don't think we quite have enough statistics to probe this very well at -13. And in fact, when you start including error bars from essentially the gravitational lensing, you start to get pretty large errors. This is at redshift 6. If you go down to redshift 7 and 8, the error bar become even larger. So it's going to be difficult. So one thing I was going to try to ask, basically the people who are working on archaeology here, and again, this is questions to Mike and other people, is what can we learn about the evolution of the volume density of redshift -13 objects from archaeological studies? How does this, based upon luminosity functions, there's a lot of evidence to suggest that perhaps the volume density of -13th magnitude object doesn't evolve a lot, say between redshift 10 and 6 or between redshift 6 and 4. What can we say on the basis of archaeological studies? Is there anything that we can say? There was a very nice paper by Mike basically showing that based upon various archaeological studies, that basically there has to be a break in the luminosity function around -13. That basically the luminosity function goes steep, then it suddenly starts to flatten off. Is there anything we can say based upon all these different, I'm just to the entire audience, is there anything we can say about the evolution of, say, sources at -13th magnitude based upon archaeological studies? Yes. Sorry, I didn't mean to give a long talk. It's a big build-up to the...
It's fine. I think I've answered your first question. I've kind of forgotten what it was.
So the question was basically, how does things at minus, how does the volume density of minus 13th magnitude objects evolve cosmic time?
All right, so I don't know if I have the evolve part. Maybe I do. Can't you get that from gamma ray bursts? I mean, we know roughly half of them are detected. On the ansatz that gamma ray bursts trace star formation, which I think is a pretty good one. We know about half of them are detected. The other half that aren't, about half of those are dusty, so they're also pretty massive, which leaves you about 20% of the star formation occurring in very faint objects, fainter than probably your minus 17. And so pretty straightforwardly, I've got the volume density of faint objects, however faint you want to make them. How they evolve over time, there's probably not enough gamma ray bursts. Well, there's not enough gamma ray bursts detected above redshift 10 to tell you that. But I probably can look at something differential from 1 to 5. I don't know if Brant's here. He's probably thought about this more than I have, but I think you can answer pretty straightforwardly.
So you would say, based on gamma ray burst, what would you say the answer is?
I'm going to contribute less than 20% of all the UV production from galaxy failure that you get pretty shallowly.
Okay, would you say it's how would you say the evolution is between, say, redshift 4 and redshift 10?
As I said, the least will peter out at 6. So I don't know.
Just asking the people doing archaeology, Mike, would you be able to gesture an answer to this question I posed about how does the volume density of sources at minus 13th magnitude evolve based upon archaeological studies?
I think it's pretty difficult with archaeology because the difference between a stellar population that formed at redshift 10 and one that formed at redshift 6 is essentially 0 in time, and that's the physical parameter that people are measuring.
But what about redshift 6 and redshift 4, or redshift 4 and redshift 3?
Well, there I think you're starting to get places, but then again, you still have the same question that Brant asked earlier, and potentially related to Eric's question of how many pieces were these local group galaxies in. I think if we can get at that, then we can start to answer these kind of questions. And so the data are there, but we need to combine it with some other things. Right now, I don't think we're quite ready to answer those things.
Do you think that you're going to be able to come up with an answer in the next year, a few years, or?
Yes. No, I think that it's certainly possible, but it needs work from a lot of angles to get that done. And JWST will help because it'll go much larger volumes that you're probing, and you're understanding more about how representative things within the Milky Way and Andromeda are.
James, do you have any? I mean, if you're good, would you have anything different to add to this?
Well,
to answer this
I guess
question?
I have a question just for you. So, are you basically saying that if, given the assumptions you've made, this striking evolution you need in order to match the Planck data and the other constraints you've added doesn't jive with extrapolating the luminosity functions all the way to minus 13?
It doesn't jive at all, and so I'm suggesting.
So, where do you have to truncate
maybe I mean, yeah, you would have to basically truncate it at minus if you want to get things to kind of match. Say you want this, you want to match the evolution of the ionizing emissivity with galaxies. You basically want to truncate it at minus 17 or minus 18, or you wouldn't want to go down that far in searching for ionizing photons, because basically, if you're searching down to minus 13 based upon extrapolations, then there's essentially no evolution.
I mean, I do think that if you're at minus 15, you could map that. I mean, at certain broad redshift bends, right? You can map that in principle down to galaxies that you can study directly in the near field. So in principle, it depends on how far you have to extrapolate and exactly what the slopes are. But I mean, at those luminosities, you have descendants in the near field. And you can't, in principle, you could provide constraints there. So I think it's possible. I mean, Mike's being conservative, I think, but I mean, in principle, this is exactly what the near field constraints on deep field science was built for, right? It's trying to do those comparisons.
Yeah, I mean, these are the sort of things you really want. I mean, there are, if you, I mean, it's probing down to minus 13, particularly at redshifts greater than 6, is starting to be challenging from things like Hubble frontier fields. And so I think that, that again, to try to answer these type of questions, it would be, again, useful to have sort of more local probes. And so it would be useful to know if your observations would agree with this or not agree with this.
We're on it. Oh, David's got a question. Okay.
It's a very simple one. That is, if I look at these big error bars that you have at that end where there's supposedly a big problem, I would think that, gee, you know, it could be just over time you'd find that, in fact, it's not a straight line. It's just some curve, and everything would be just fine. Is that totally out of the question?
These big error bars are based upon extrapolations of field results. I think that the frontier fields are sort of are confirming this. And I think that different people are. Again, I'm showing this because I think that in a few months, maybe people are going to be making claims that that each of these things are going to have smaller error bars, and that's what the Hubble frontier field observations are finding. So, including ourselves. So,
You're anticipating a problem.
I'm anticipating a problem. I'm anticipating a problem. But I mean, again, I think that maybe Steve will answer for himself, but my guess is that this is the reason that basically in their model, they actually require quasars in their model to actually match, to essentially try to match a somewhat steeper evolution.
Can I ask a completely different question, or is it?
Okay, yeah, sure. Ask a different question.
Good, because I have a real problem with these ultra diffuse galaxies. You know, whether you basically ask Avishai or me, I think all our galaxies and the path of galaxies of star-forming disks will always rotate. There's no other way, because you form stars always in a rotating gas disk. So if you puff it up by whatever process, you will form something flattened, somewhat flattened and rotating. And I just wonder if this is a clear evidence that the ultra-diffuse objects are not rotating. I have no way to form them by any feedback, unless someone got it without any rotation. Yeah, but spheroidals, yes, same problem. If they would not rotate, how do you form them?
They do rotate, but once you pump in energy in, so vertical
Yes.
velocity increases, rotation velocity is the same, so V over sigma is different.
Yeah, different, but still existent. It's not zero.
It's not zero.
Yeah, and the observations show zero.
No, they don't show zero, 0.1, and they couldn't even possibly measure.
So,
Secondary kind of,
and this, yeah.
I mean, those things don't form in any of our simulations, they don't exist.
Exactly. So you have a problem. Well, this is not the problem with nature. Yeah. Well, you make it happen. Next year we'll have them. Sure.
So I think we only have like 1 minute.
So do you want to raise some things? I mean, the only thing I have to talk about is like these ultra compact.
Yeah,
galaxies.
I have one question I was going to raise that's related. That's basically on this point, and I guess it sort of goes like this: are these ultra diffuse galaxies like just sort of an interesting eccentric population we want to try to figure out how they're made, or do they represent some kind of fundamental change? Is it going to really shift the way we think of galaxy formation? And this is why I think this. Wait, hold on a second. Wait. So we heard that basically 1 in 10 to the 8 stellar mass galaxies fall into this class. And so I think if it was 10% at fixed stellar mass, you might think, oh, you know, they're sort of an oddity. We'd like to understand 10%, but it's sort of at the threshold where I might not freak out about it. But if they're sitting in 10 to the 11 solar mass halos, 1 in 10 at 10 to the 8 means that it's basically half and half. You know, half of the 10 to the 11 solar mass halos have this class of galaxy in them, and the other half have like 10 to the 9, 10 to the 9.5 galaxy halos. And if that's true, that means it's a big deal. Like, this is not an oddity. This is like a whole class of formation that we don't understand. So I wonder what people think of that. And I thought the velocity dispersion of globulars too.
Well, also the dynamic capacity. We do have a spectrum of one star. Yeah, we get the velocity still in the stars. In that case, it's
That was 70 kilometers.
yeah.
70 kilometers would be small.
Well, that's getting pretty big. That's getting pretty big for more.
Yeah, it's a big instrument more, but not really.
I mean, it's an LMC, right? I mean, it's an LMC. LMCs are pretty big. I don't know. Not that anyone has an answer, I guess, but it's weird. Yeah, it's all. So the only thing I get, they're 100% accreted. The main halo didn't form any stars, and they're just stellar halos. They're just ghosts. They're just the stellar halos.
And so,
It doesn't matter. It's a large.
It's crazy. It's weird, but
Even it's a 1%, it's still enough.
so what? And on the other extreme end, the ultra compact dwarfs. I mean, what kind of what fraction is? Those are a pretty small fraction of star
that's
formation.
easy. That's gas dissipation. All right, I think everybody's hungry. So we